Hello everyone, in this video we'll be looking into something called as combinational gates. So we have seen some fundamental gates which are also called as universal gates. So lot of combinations can be used with those fundamental combinational gates, that is AND, OR and NOT, apart from these, and NAND as well as NOR gate. But however, these combinational gates have a huge applications in electronic industries and some when you are planning to write some logical things. So these things are very much useful. So let us switch to the combinational gates. But before going to these combinational gates, we can have some more variants of the multiple input gates. That means a gate in the previous case we have seen having two inputs, but technically in real time we don't actually limit ourselves with the two inputs, that is x and y. At times there could be x, y and z as well. So the output equation in this case, since it is a OR gate, so the output equation is like a combination of these three inputs. Similarly, AND gate, it is the same thing, and we have some more things, that is two inputs with one output as a complement. That means internally we have a combination of these two things, that is AND gate as well as a NOT gate here as well. Like so the internal component will be made something like this. So these are special type of gates where they have more than three inputs, or in certain cases more than five. Like you can perform the same operation using this special variant gates. So coming to this combinational logic, that any gate that has been used, okay, so it should follow only the Boolean functions. Apart from Boolean functions, it will not go like out of the boundary. For example, you take this fundamental function, which is a function of x, y and z. Whenever the thing is given like this, you should consider, so the function is made out of these three variables only. Okay, these three variables are actually bounded to 0, 1 in case of a digital logic, where the output equation is equal to x plus y complement into z. Okay, so you just make the things very clear. So we have x, y complement and z. So how would you make this combinational circuit? It got an AND gate and OR gate. Okay, apart from that, since the complement is given, we require three fundamental gates. So you keep an eye like which and all things that are required. So here there is one plus symbol. So what kind of gate it is? OR gate. Okay, AND gate. X plus, which is OR gate, then AND gate. Okay, so we require three gates, and this is one complement, this is NOT gate. So this is a very fundamental thing which everybody should understand. So here, so I have taken x, y and z. Okay, these are the three components, where initially itself we have made y as a complement thing. That means we have used a bubbled NOT gate. Okay, bubbled NOT gate, where the direct input itself, where here it is y, so the input itself is y complement or y bar. Okay, and z, whenever it is being fed to this thing, that is y and z, and x is being given as an input to an OR gate, where x or y complement or y bar into z, where the output will be realized in this fashion. Okay, for this let us start making a truth table. So you take three components. So since there are three inputs, what is the maximum number of combinations you will get is 2 to the power of 3, which is equal to 8. Okay, so we can write in this fashion, that is x, y, z. Okay, so we can make three things like this. Next, the thing is y complement. Okay, so that's the least possible thing, y complement, followed by y complement into z. Okay, the final column would be, that is x plus y complement into z. Okay, make sure that you make a dot or something so that it will be easy for you, but it's not required all the time. So the combination will go something in this fashion, that is 0, 0 and 0, 0 0 1 1 0 1 0 0 1 1 and 1 0 0 1 0 1 1 1 0 and triple 1. So these are some combinations what you get. Okay, right. So let us take only the y complement, which is 1 1 0 0 1 1 0 and 0. Since the space is not available, I'll just strike out this thing. So what is y into z? That is this y complement into z, that is 0 into 1, that is 0, 1 into 1 is 1, and then followed by 0 into 0 would be 0. Okay, and then 1 into 0 would be 0, 0 into 0 is 0, 1 into 1 is 1, then 0 into 1 is 0. Okay, 0 into 1 is 0. Okay, like this you can proceed it with the x plus y complement. So this whole term, okay, what you are supposed to do is just add it to the x, that is, let us talk about the first term, 0 plus 0, which is 0. So I am writing the final equation of x plus, okay, y complement or y bar into z, which is 0 plus 0, which is 0 here, followed by 0 plus 1 is actually 1, then followed by 0 plus 0 would be 0, then followed by 0 plus 0 would be 0, 1 plus 0 is 1, okay, and so on. You can make the truth table. So whenever you are exciting individual components, so you have to get this output. Okay, this is the truth table realization. Okay, whenever you are planning to realize your output, it has to be realized with a truth table. So while a question is given like this, realize the truth table or make a circuit. Okay, so this is a kind of a complex form, but whenever it goes to larger equations, this will look as simple as it is, but when we go for a larger combinations, it will be very tough, right? So like this you have to frame the truth table. Similarly, in certain cases it will be given with so look at this example. So in fewer cases, or maybe in larger cases also, at times you'll be given with a figure and you'll be asked to make the equation out of the figure. Let us check this figure. It got 4 inputs, so the combination would be 2 to the power of 4 combinations, which is equal to 16 combinations you will get for the inputs. Similarly, look at z. So for example, if you want to make the equation for z, okay, we have to start from the leftmost part, that is, take the two individual inputs with the AND gates and then followed by combining them with OR gate. So the equation would become A into B. Okay, we got the first thing, which is here. Similarly, C into D, which are added at this end. Okay, which are added at this end, so that will be a added thing. So Z is equal to A into B plus C into D. Let us check the combinations here. We got like four inputs we got, so we got 16 combinations, where the last combination would be 1 1 1 1, which is realized by Z, that is A plus B, A into B plus C into D, that is we are adding them together. So you know that these combinations, it's very easy to understand, so you can have a look here. I'll finally go to the Z part. So that is A plus B, A into B plus C into D, that is the Z value, right? Okay, so that is 0 plus 0, it has already been made. So 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 1 is 1, and 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 0 is again 0, so 0 plus 1 is 1, and continue till the end. So the final value would be this thing, where both are 1, so that is 1 here. So like this you can make different combinations. Either you'll be given with an equation, or you'll be asked to derive the equation for this thing. Okay, so that is how we can make the combination logics. Now we'll discuss about switching algebra. Okay, so now we in the earlier case we have deal about the different combinational logics, where combination of and, or, not, and at times XOR and NAND and NOR will be used. But in this case, where switching algebra will always deal with two level logics. Okay, we already know it. Okay, the first thing is sum of products or product of sums. That is, sum of the products means you are adding two things. In the previous case we have done a into b plus c into d. That is basically product of sums or sum of products. Okay, so the first case you just have a look. Sum of products means a into b. Okay, there are two products which are summating together. A complement into c plus a complement into b. That is the sum of products. That means whenever two or more multiple variables, that is a, b, c or d, are getting multiplied and added together, that becomes a sum of products. Similarly, we have product of sums. That means we'll multiply two or more elements which are being added together. That means a complement into c, a complement into b, a plus a complement in plus c into a plus b complement into a plus b plus c complement. This is basically product of sums. This is very important. Both are very important things, that is sum of products and product of sums. Second thing is multi-level logic. That means whenever multiple layers, okay, of two level logic things are being utilized. Just an example, you just have a look. That is, first thing is a plus b into c complement plus ab complement ab complement. Okay, the whole thing is being added together with b complement into c plus c complement into d, and the whole complement, the whole equation is being complemented, okay, into bc plus c complement into e. This is called as multi-level logic, okay, or multiple level logic. Okay, so generally in case of any digital logic design, whenever you are planning to design a chip which performs some digital operations, okay, so first thing is we have to consider certain things. The very first thing is multiple outputs. First thing is multiple outputs. So the circuit, whether it is giving multiple output or a single output, that thing has to be very specific. Second thing is don't care sets. Don't care sets are something like which are not being utilized in our thing, but still they are a part of our equation, right? Still they are a part of this equation. That means whenever you are just solving this whole equation, okay, these individual states, this is one state, one complete set of output, this is one set of output. When they are adding together, at times we don't require certain outputs, okay, so eliminate e in this case. So wherever there is e, it will be eliminated. That's a kind of don't care set. Okay, then we have certain handy tools. Those are called as laws, which will actually help us. Okay, the very first one is DeMorgan law, consensus theorem, Shannon's expansion, truth tables. Okay, truth table we have seen multiple times while looking into those fundamental gates, combinational logic we have seen. And when we want to reduce, okay, when we want to reduce this combinational logics to a smaller output, okay, just in the form of sum of products or product of sums, okay, we use k-maps. Okay, k-maps are basically used when you have single output, mostly single output, and the logic is of two levels. There is no intermediate logic. Those are called as Karnaugh maps. So coming to the next one, there are certain rules. Okay, there are certain rules where any Boolean logic or Boolean algebra has to abide. Okay, these are called as axioms. Okay, so these axioms are basically it's basically a statement or a proposition which is regarded as being established. That means these are certain laws basically which are already been established and accepted universally because there is a valid proof for them. There is a valid proof for them. Okay, so when these proof will be valid, first thing is B should be a non-empty set. The set of values should be non-empty. B is basically a non-empty set. You know what is fundamentally sets are meant for. It's basically a combination of data types or datas in a simple fashion. Here these data values are two distinct elements. Be very just keen on this. This is this B set. Okay, B, if I just open it as a set, so it got only 0 and 1 as the elements. So the elements of this particular set should be 1 and 0. Then only these laws are applicable. Not only B, any typical variable which got two states in simpler terms, it is called as a state. Okay, so the very first thing is commutative law. This law states that whenever two or more variables are added together, okay, that is, let us assume A and B, when they are adding together, it is equal to, okay, the reversal of the thing. That means if A and A is added to B first, okay, there is a high possibility that it can be added in a reverse way. For example, A is equal to 0 and B is equal to 1. Okay, so when you just check it, that is 1 plus 0. So what is the result? Basically it's 1. So this is called as commutative law. This law is already there existing in the system, and it can be applied to multiplication as well. That means and logic. Okay, multiplication also it is required. Okay, and addition also, this is more applicable. Let us look into this where multiplication is there. That is, first thing is we have verified with OR logic. Now we are going with AND logic. Okay, so that is, let us assume 1 into 0. 1 into 0 is basically 0. The same thing, I am just making it 0 into 1 would be again 0. So it is basically a kind of proof. Okay, so let us check how does this can be verified in the later slides. Next thing is distributive law. The next one is distributive law. Distributive law will states that whatever way it is being distributed, it has to be properly distributed among individual components. That is, if A plus B into C is equal to A plus B into A plus C, that is what it has been happened, right? So that is A plus B into C. Okay, if you take, since it's been taken as this thing, it can be made in this fashion. That is A plus B, so it is equal to A plus B into A plus C. That is what the proof is. That means whenever you're taking A as common, okay, so that will be the same thing, right? It has been applied in OR logic here, and in AND logic also this is possible. That is A into B plus C, where it is equal to A into B plus A into C. Similarly, we have one more law which is called as identity law, that is A plus 0 is equal to A. Similarly, A into 1 is equal to A. Okay, so the here our logic has been applied, here and is been applied, right? Complement law, that means A plus A complement is equal to 1, whereas A into A complement is 0. Let us check it. A is equal to 0, so 0 plus 1 is equal to 1. That is very much proved. Similarly, if you take it the reverse way also, it is possible. You just apply the same thing here. A is equal to 0 into A complement is 1, so 0 into 1 will be equal to 0. So this is basically complement law. So all the Boolean logic will work on these 4 laws only, right? Any Boolean logic you consider, it will work with these 4 laws. Let us have a review of this. I have already discussed it. Okay, how to take this distributive law. Okay, identity law is very simple to prove. I am not going to teach upon those things. We'll start with distributive law. It states that, okay, in 2 forms we have, one is with AND form, other one is with OR form. Okay, we have seen it here, distributive law. First one is OR form, second one is AND form. So here the first is AND form will take. Okay, so how this can be checked, how this can be verified? That is A into B plus C is equal to AB plus AC, right? So that is A, B and C. We got 3 combinations, so we'll be getting 8 combination, since it is 2 to the power of 3 based on inputs only. So we can actually check. Okay, for one particular thing I'll just give you the proof, rest all you can give a try on yourself. So b plus c is basically ORed here. Okay, that is what it's been given, and a is given directly to an AND gate, right? So we'll take one logic 0 1 0. I'm just taking 0 1 0 for this thing. How we can make it, that is, so a into b plus c. First we'll take b plus c, okay, then a into b plus c, right? First, what is b plus c? B is 1, so c is 0, so b plus c would be 1. Okay, a in this case it is 0, where the whole equation should turn 0. Okay, that is 0 into 1, that will become 0. Let us talk the expanded form. Okay, ab into ac. For this particular thing, the diagram would look like this. You got 4. Okay, but technically it is the same thing. Okay, don't consider common inputs, so this is basically not required in this case. So here also there are 3 inputs, so you will get 8 combinations. Let us check this thing for the same combination, because we are giving the same inputs now, so we have to check with the same combination, right? So this is AB plus AC. Okay, AB plus AC. So let us take the same thing. So A, B and C, which is 0 1 0. What is AB? Then what is AC? Then adding up of AB plus AC, right? So AB would be 0, AC would be 0. Okay, so 0 plus 0 would be 0. So in this case, this and this terms are equal. That means hence it is proved, right? This is about distributive law pertaining to which thing? OR logic. Okay, or is it OR logic or AND logic? Basically it is AND logic only. In this equation we are just adding up the things together. When it comes to OR logic, it's basically in this way you have to make. Okay, here it is ORed. Okay, it has been ORed, A or B plus C, right? So here let us check this equation in OR form. Since more number of OR gates are used, you can consider this form as OR form. More AND gates are used, so it is AND form. So it is very simple like this. Okay, let us check with this thing. How to solve this? Let us assume the same combination, that is A, B and C. Okay, we'll just make the whole things in a single table, so it will be very easy. So A, it is BC, A plus BC. Okay, last case it is A plus B into A plus C. This is A. Okay, so that is 0 1 0. I'm just taking the same combination. So BC would become 0, A plus BC. Okay, BC is 0, so A is actually 0, so that is 0, right? Similarly, we have A plus B into A plus C. What is A plus B? So A is 0, B is 1, so that is 1 into A plus C. A is 0, C is 0, which is equal to 0. So 1 into 0 would become 0, hence proved. Okay, so this is how you can make the proof for distributive law. Okay, it's a very important law. This might be a very important question for your major exam. So we'll go to the next part. Okay, so here it is basically called as associative law. Okay, we were discussing about 4 fundamental laws. Okay, apart from these 4 fundamental laws, we have one more law called as associative law. In this associative law, what it states is a combination of OR between A and B and C is equal to A or B plus C. Okay, that is A plus B whole bracket together plus C is equal to A plus B of C, right? Okay, so that is called as law of associativity. The same thing is possible with both and OR logic. In the first case we have seen with the OR logic, that is we got 3 inputs, it is OR together, out of which A, B and C are OR together. That means the output would be same thing, right? So let us assume this as A, B and C. So let us check for one particular combination. Now I am checking it for 1, 1, 1. Okay, right. What is A plus B? A plus B is 1 basically, plus C. A plus B plus C. A plus B plus C, which is basically equal to 1 plus 1, again it is 1, right? Now similarly this can be done with the same combination. Okay, both are nothing but the same gates, but only the inputs were varied. Okay, so if you check for this also, you will get the same output. So this is one proof. Similarly we have AND logic. In AND logic, combination of AND is used. Okay, so associativity law will states that how one particular set of elements are associated with another particular set of elements in a digital logic. Okay, so the next one is the DeMorgan's theorem. It's a very important theorem. No matter wherever you apply this, it is very important. According to DeMorgan's law, what it states is, whenever two or more elements are ended, okay, two or more elements are ended, okay, their combination of complements, so and complements, is nothing but OR whole complement, right? So how you can solve this? Okay, so you can have a look. So there is a bubbled AND gate and a bubbled OR gate. Okay, basically whatever the inputs that goes to this will be, it's basically Y complement is A complement and B complement. So the bubbled nature is basically not. Let us check for this. Okay, so A, B, since there are two inputs, I am just taking one or two combinations. I am just taking 1 and 0 as a combination. You can check it for all possible combinations. Since there are two, okay, you can go with all four combinations. You have to go with all four combinations. So that is 1 and 0 I have taken for time being. So what is AB complement? First we will take AB followed by AB complement. Okay, AB whole complement. The whole thing I have to come. A 1 into 0 would be 0. 0's complement would be 1. Okay, let us check A complement plus B complement. A complement is what? Plus. We are basically adding together. Okay, A complement is, which is 1 and 1. When you are adding them together, that is A complement plus B complement, which is equal to 1. Hence proved. Okay, so this is the AND statement equivalent to OR. Similarly, OR should also be equivalent to AND. Okay, first case it is OR equivalent to AND. Okay, similarly AND will be equivalent to OR. Okay, that is the second statement of DeMorgan's law. Okay, so let us check for this also. The same thing in a reverse order. A complement into B complement is 1. We have already taken. So let us check for one more combination. 1 and 1 I am checking. A into B. 1 into 1 is 1. A plus AB whole complement is 0. Okay, right? A complement is 0. B complement is 0. Okay, AB whole complement I have written as 0. A complement B complement, when you are adding together, here it will become 0. So 0 is equal to 0, hence proved. Okay, the same combination I have taken it in a reverse order. Okay, so that's all for this session. Thank you. Thanks for watching.